decreases by increasing temperature, while this one is not affected. So it may happen that at a certain point, the tendency is inverted. But you see that this happens about 1,000 degrees. So this is very far from normal conditions. So in normal condition of our engine that we are here, the efficiency is much higher. So let's see. Let's summarize this again. Let's see what is the comparison between the two systems that we have examined so far. We have discussed so far about batteries, like lithium batteries, and you know that the lithium battery is a closed system. The battery that you have in your cellular phone is closed into a container, right? And what will happen that this battery will go on until all the all the materials inside are consumed, and then you cannot work your telephone anymore. You have to charge back the battery. Fuel cell is an open system because the component are hydrogen and oxygen, so they can come from outside. And the fuel cell is not really a rechargeable system. It's a primary system, but it continues forever until they get hydrogen and oxygen. That is, but both of them are systems which convert chemical energy from electric energy. Okay. And then we have this is, I repeat again, because it's important. As I say, fuel cell may have some in common with internal combustion engine, but of course we have the big advantages of increase in energy efficiency. Okay, so why now we have to understand why these fuel cells are not yet on the market, and now we have here what seems to be in a fuel cell. I make again a drawing, which of course is exactly the opposite of electrolysis cell. Okay, in the fuel cell, as we have seen, we have one electrode we can call again A1, another electrode which is called A2, okay, and then we have an electrolyte, suppose an acid electrolyte, okay, and actually what would happen here, you remember, is the oxidation of hydrogen. So here we have hydrogen, which comes, and it becomes H+, okay? And on the other side, we have the reduction of oxygen. So oxygen comes here, okay, and becomes H2, and we have some electrons going here. All right. But let's consider a little bit this situation. This electrode is not like a normal electron, not like lithium. For instance, if we have a lithium cell, a lithium battery, okay, I think we can cancel that. We understand that it's just the opposite. In the case of a lithium cell, you remember we may have lithium, and here may have, for instance, titanium disulfide. So here the electrode itself is an electronic conductor. So this electrode may produce electrons, because remember the reactions here is lithium goes L plus an electrons. Because lithium is a metal. So lithium by itself is conducting the electrons through the circuit. And then here we have the lithium plus titanium disulfide become, lithium TS2. Also this one is in a way a conductor because we mix with some carbon. So also this one is able to receive electrons. So there is nearly no problems here because we have the electrode materials which are conducting. Now in this case the electrode material is hydrogen, is a gas. So how can we conduct with gas? We necessarily require the help of some metal electrode which may drive this reaction. Okay? Is that clear? But these reactions are not so easy as I wrote here. You know, these are the reactions which are electrochemical reactions which are the most studied in the world. But still there are some problems there. Because this electrode, which I may call M1 or M2, is not just a simple way of collecting electrons and distributing electrons, but is very important to drive the reaction. Because, as we will see, this particular electrode helps on going on the reaction. And in a way, it catalyzes the reaction. It's a catalyst. It's an electrocatalyst. So let's take, for instance, examples of this electrode here. You see, I write this reaction like this, but it's not that easy. Because what will happen here, maybe I can cancel this. Here we have this M1. Here we have the electrolyte. This will be M2. Okay, here we'll have some hydrogen arriving. Okay, so let's see what happens here. We'll enlarge this now. This is the interface on M1. So what will happen is that this M1 will give some electrons here. Oh no, sorry. In this case, okay, we are talking now about the opposite reaction, but it's the same. This M will give some electrons here, and maybe H plus will receive the electrons. But what will happen after he has received the electrons is that this H is adsorbed on the surface. Okay. Then, to produce hydrogen, suppose that now we have two of these hydrogen atoms adsorbed, to form hydrogen gas, these two have to combine together and become H2. So the process here implies first the absorption on the substrate and then the release of the substrate. This is written here. So this will be the situation, for instance. This is for a reduction of hydrogen, just the opposite. But you can turn in the opposite direction, then you have oxidation. Same problem. So you have these electrons, we are coming from M, which is the metal substrate. And you see you form this absorption. Then the hydrogen which is absorbed has to deabsorb. So in a way, in the first the metal substrate get the hydrogen, but then he has to give it back. All right? And this may happen in two ways. So you understand now that if M, this substrate here, has a very high tendency in absorbing hydrogen, maybe forming some hydrides, also chemically, then this step will go very fast. But then this step will not go on because the hydrogen will remain there. Okay? Now suppose the M instead has a very high tendency to deabsorb hydrogen, then the second step is very fast, but not is the first step. So what you have to do, you have to find something for M which has a compromise, which has enough affinity for hydrogen to absorb it, but not so strong that it cannot be released. Now, if we go to look at this, I think, well, we go back to this one. You see that if we report here here we report the affinity of forming MH, and here just the important electrocatalytic activity by the same is the other the affinity of, I mean, the power of releasing hydrogen. So if you take this, for instance, material, titanium, will be very good, doesn't cost too much, but unfortunately titanium is a very weak M bonding strength. So these the first step will not go. If you take tantalum, which is also a good cheap material, we will have very strong AMH bond strength, but that means that hydrogen cannot be released. So neither this one or this one will operate. Only the one we are in the middle are good catalysts. But unfortunately, look who is the good catalyst here. Platinum, rhodium, gold. So unfortunately, modern nature tell us that for making a fuel cell operation at the hydrogen electrode, but we see also the same thing happen to the oxygen, we need as a catalyst a very precious metal. And you see, if we want to have a fuel cell at low cost, of course you must have some conditions which our electrode must be stable in the range of operation potential, of course. They must have a high surface area to promote the reaction. High exchange current density means high catalytic effect, and also low cost, of course. But and you see, this is what I was telling you before. Unpaired d electrons, but oxide-free surface, not too strong and not too weak chemiabsorption bond. So this hydrogen has to be absorbed on the metal, not too strong, but neither not too weak. And obviously, platinum is not a cheap material. And we will see, however, that we have some way of reducing the cost, because we can use very little platinum, but this will be discussed in the next lecture. Okay, same thing happens for the oxygen electrode. So these curves are very famous, very common, very well known in kinetics. Are called volcano curve because these are shaped like a volcano, and the only thing we work is the top of volcano when you have this evolution. So also here you have I don't understand. Here I have also the oxygen electrode. We have the same situation there. In this case, however, the absorption is produce some oxide, and then what will happen, you will have some decomposition of this oxide with the formation of oxygen. Basically the same way. And you see that also in this case, we are a bit better here because maybe we can use manganese oxide, but the best catalysts are iridium or ruthenium.